Yeah, as mentioned, my name is Isabel Groß. I'm application specialist for microscopy at PicoQuant, and today I'm going to introduce new analysis options to push the limits of FLIM imaging modalities and the software tools that we can provide to go for that. So first to say the software I'm going to introduce, or the software tool, is based on the software that comes with our single photon counting confocal microscope, Luminosa, but it can also be used by all other PicoQuant systems and also LSM upgrade kits that use PicoQuant FLIM kit. So if you have a Zeiss or a Nikon or Evident microscope with a PicoQuant kit, you can also use the software I'm going to introduce today. The Luminosa microscope in generally is designed with a focus on biophysics, and before you start to cringe over the word biophysics, it's also designed to make these biophysical applications more easy, more accessible, also, for example, in facility environments. So the software, especially the software solutions, designed to make it more accessible, especially the analysis part. So these biophysical applications include single molecule FRET, FCS, single molecule imaging, but also other imaging modalities like FLIM, FLIM-FRET, anisotropy. And today the focus will be on fluorescence lifetime imaging FLIM. So confocal FLIM, generally a very nice method that is quantitative, it's reproducible, and with our microscope, but also with our software solution with just a few clicks. So FLIM used to be a method where people were, it was supposed to be or said to be complicated, especially on the analysis part. You have to know your data, you have to know what you're doing. We're trying to improve that and make it more easy, more accessible. In the Luminosa, for example, the microscope itself is designed to be for highest sensitivity, hardware bias, especially for single molecule research, but also for FLIM. We need to collect single photons, so we need this kind of sensitivity. FLIM also used to be a, let's say, rather slow imaging method because you need to collect enough statistics to get a nice to get enough data to analyze it afterwards. But nowadays the hardware is possible to do rapid FLIM, so we can do video rate FLIM imaging of dynamic processes as well. In our systems, we use hybrid PMTs or SPATs, and now very new also a SPAT array that can be combined with fluorescence lifetime imaging. And on the software side, we use GPU accelerated algorithms that can offer online preview of the data. I'm going to show that in the next slides, and also InstaFLIM automated analysis, so you can directly see the analysis of your data. And generally, it is based on context-based workflow. So if you select an application, the software and the hardware is set up for that application specifically, so you don't have to worry about that. Okay, InstaFLIM during data acquisition, what I just mentioned. So during the measurement, as you can see here, you not only get the average lifetime image, of course, but you can also get a fluorescence lifetime histogram directly during the measurement. You have a time trace during the measurement of the intensity and the TCSPC decay. So you can directly see if this is the right position, if your settings are right, and if it's worth continuing with acquiring the data. On the analysis side, so after acquisition, you can open your data and then get an instant analysis and quality check of the data, which means you have automated fitting. So by opening the analysis part of the software, you directly get a multi-exponential fit and fit rating. These are the little stars over here, fit rating of your data. So there's no need for user input on that section. So directly there is the analysis run. There are multiple analysis options. I'm going to show them in a second. And again, this is enabled by GPU accelerated algorithms. So we're going through the analysis options that you have. I already mentioned that you have multi-exponential decay fit with fixed or variable lifetimes. This is done directly by opening the data. You can adjust the parameters, you can adjust the lifetime components that you want to fit, and so on. And you directly get also an image with those fitted components already. On the other hand, we have multi-species pattern matching included that you can also use. Then there is the phasor plot included and a lifetime histogram as well. So 4 different analysis routines that run in parallel. It suggests you for FLIM species separation the best fit, and parameters can be fine-tuned. And the good thing about this is that all of these methods are connected to each other, so you can have like a holistic approach to analyze your data. What I mean by that is no, sorry. So what I mentioned in the beginning is that it's not only for the Luminosa data, but you can also use Nova FLIM. This is the analysis, let's say the analysis add-on for the software that you can also use with the PicoQuant system LSM upgrade kits, where you have the same benefit of this holistic approach to analyze the data. But on top of that, it offers advanced and flexible ROI handling and batch analysis, which is also very fast due to the GPU accelerated processing. Also, we offer enhanced metadata and data export options. And for the ROI handling, for example, we have included this 2D histogram plots where you can put different variables together and get a plot where you can also see different populations. In this case, intensity over the average lifetime, and you can like select an ROI in the histogram and directly get this ROI in your image for exploration of your data and further analysis. This is an example to show you how this is connected. So if you, for example, select an ROI in this 2D histogram plot, you can see directly the results in the phasor plot as well. So here, for example, on this ROI, you have seen that the phasor plot changes directly. So they're connected to each other, and you have a analysis options on multiple techniques. For the batch analysis, this is for Z-stack, for example, for time-lapse series, for stitched images, so large data sets that, again, you can directly get an initial fit, and then you can do a batch analysis over all of the images of your frame. In this case, for example, these cells were stained with FLIPper-TR, a marker that changes lifetime with membrane tension, and then you can do a time series. For example, people are doing hyper or hypoosmotic shocks, and then you can see that in the batch analysis we can print it out over time. So you can see, for example, lifetime changes over your time series, percentage of lifetime in component 1 changing, the average lifetime changing, and so on. And this is done over the whole image, and then also over the ROIs that you have selected in parallel. So you directly get both data sets. I mentioned in the beginning, so we use open data formats and enhanced metadata, so you can view and search measurements and analyze settings down to the raw data. You have a convenient export to text file in XML, and the enhanced metadata is available even for OmeoTIFF. It's possible to export and import ROIs, and this is in the way that it's compatible also with open source software, like, for example, Flute or FaserPy. Another new, I mentioned in the beginning that we have a spot array that is connected to the Luminosa, or it is implemented in the Luminosa now, which offers confocal FLIM with more resolution and more contrast. So the idea is to use an array detector with an open pinhole configuration, but then use the array as their own, let's say every spot of the array as their own pinhole, and then gain enhanced contrast and increased resolution. And in our case, we combine that together with lifetime contrast. This is in collaboration with PicoImaging, so the spot array comes from PicoImaging, and then we offer the multi-hub 160 TCSBC electronics with enough channels to include lifetime for every of these 23 spots in the spot array. This is an example measurement here, so you can see on the left side the sum of all 23 pixels, so pseudo-confocal image that is taken. Then we do in the software pixel reassignment to gain around, let's say, 30% more resolution already. This is done implemented in the software, so you don't have to adjust that. You can, but the software suggests a pixel reassignment automatically. And then also included in this Nova ISM add-on, we have computational sectioning, so we're separating out of focus and inner focus light, and then you can use the inner focus light image for further analysis. And then on top of this inner focus light image, you can do a deconvolution that is also integrated in the software to gain another 30% more resolution. And of course, this is not this is nothing that is invented by us, but what we include now is the fluorescence lifetime part of it, so you can directly get the lifetime information in those images, also in the computational sectioning one, and then you can go on with your lifetime analysis after the computational sectioning, for example, and even do a deconvolution in the end. Here you can see the comparison between out of focus and in focus light, so the computational sectioning, and then you see that you get an extra layer for the in focus part, and you continue the analysis on that part. The deconvolution is also in the Nova ISM integrated, so it's a one-click deconvolution that has an automatic parameter estimation, but if you want to adjust the parameters, of course, that is also possible. And then you gain another contrast improvement, as you can see here. So this would be reassignment of the pixels, computational sectioning, and deconvolution. I brought an example just to show you how it is if you use multiple markers. So in this case, we have 5 different markers, and they are separated by the excitation wavelengths, but also by lifetime. And then we can have these nice higher resolution FLIM images together in to extract 5 different markers in one image very easily. On the last slide, I want to give a little bit of an outlook. What we're working on is fluorescence correlation spectroscopy with FCS, with the spot array. So generally FCS, a method where you can observe dynamic biomolecular processes that influence the fluctuation in fluorescence intensity. So a molecule is diffusing through the confocal volume, and we're measuring the fluorescence signal. And then if the concentration changes, the size, the interaction of that molecule changes, you can measure that and you can see that. You get this correlation curve here where you have on the one hand a concentration and on the other hand a diffusion coefficient, so the speed, let's say, of the molecule. And this can be used in various applications, like for example viscosity in viscosity analysis, co-localization, binding assays, and so on. And for the spot array, it could be used, for example, for spot variation FCS. So we can access all of the arrays in the spot individually. So you can choose the volume that you're observing. And we are at the moment we are still trying those techniques. And you can see that there are different possibilities to use spot variation FCS. If you want to look like at hindered diffusion or at dynamic partition processes and these kind of things, where the spot array can be very useful. And dual focus FCS, usually a technique to get more precise and more or very precise determination of like diffusion coefficients. Usually you would use 2 laser lines for that, the same wavelength as the Nomarsky prism. You have 2 confocal volumes with a very specific distance from each other, so that you can get these more precise results. But in the case of the spot array, of course, we don't need a second laser because we can just use 2 of the spots in the array where we know the distance of each other, and then we can also do dual focus FCS. And then lastly, directional analysis towards flow. So of course, again, we can use 2 different or 2 spots in the array and then measure bidirectional cross correlations and fit them to forwards and backwards in the direction to see if there is any flow or any movement going on. So this, of course, is pioneered also by Zeiss in the dynamic profiler. But these are things we're working on also to implement it in our software for the Luminosa microscope, for example, to have it accessible. The microscope itself has some other nice features. So if you're interested to know more what is in the toolbox, especially for single molecule applications, but also for FLIM, you can reach out to me or to Frederick, or just check out our webpage to see what else can be offered. And this is the team working on the development of the instrument, but also on the software solutions that we offer. And with that, I want to thank you for your attention.